Hey, let's do a quick little review for the second semester final exam. And what I'm going to do is just a quick refresher on all the different topics. This should guide you in making your equation list. This isn't necessarily comprehensive. I would study your unit summaries that I had you write, and so on. There's one unit I'm cutting out of the final. We're not going to have any gravitation problems on this final, so you're welcome. But we are going to have the first part of it. We're going to start with momentum. So let's review momentum. And now, momentum, you're going to need to know basic definitions, all right? Like how is momentum defined? But let's start off with Newton's second law. We said that the net force on an object is equal to an object's mass times acceleration, right? Old faithful here. But acceleration is the change in velocity over the change in time. And so what we did in momentum is we just rearranged Newton's second law to this. For the net force times time is equal to the mass times the change in velocity of an object. Now we define momentum to be mass times velocity. So remember that P is equal to mass times velocity. So therefore, this equation, this is the impulse momentum theorem. This was called impulse is force times time, or the net force times time. And that's going to be equal, well, mass times velocity is momentum. So mass times the change in velocity is the change in momentum. So you're going to have some impulse problems. This is impulse. The impulse on an object is equal to the change in momentum of that object. So I might give you an object with a certain mass, like a force is applied to it for a certain amount of time. You take the product of force and time, you have impulse, and now you know how much the momentum changed. So you can solve for that. And that's the kind of problem that I will put on there, the impulse momentum theorem. Then we're also going to deal with collisions. We're going to have elastic and inelastic collisions. Make sure you know the difference between elastic and inelastic collisions. Now in a collisions, you got two objects, object 1 and object 2, and they are hitting each other. They're applying forces to each other. But Newton's third law says this, hey, the force of 1 on 2, the force of 2 on 1, those forces are equal and opposite. For every force on one object, there must be an equal and opposite force on another object somewhere in the universe. That is a law of nature. There is no exception to Newton's third law that we've ever observed. Well, and these interaction, this interaction force happens at the same time. So the time interval for this force is the same as the time interval for this force. And what does that mean? This is equal and opposite impulses. Well, that means equal and opposite changes in momentum for the two objects. And as long as these are the only forces acting, as long as there is no net outside force acting on these objects, well, the change in momentum of this is equal and opposite change in momentum of this, so there's no overall change in momentum, which means that the initial momentum for the whole, before the collision has to equal the final momentum after the for the entire system. So you will have a collision problem and you will have to use this idea. Remember, this might be the initial momentum is m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. Okay, and so these are equal. Now, remember that velocity is a vector. Now, it's all going to be along one dimension, so you call the right positive and to the left negative. That takes care of the vector nature of those velocities. And maybe they've stuck together. Maybe I'll give you a perfectly inelastic collision where the two objects stick together. If they stick together, then this and this are the same. So you can just go m1 plus m2 times the final velocity and solve for that. Okay. So anyway, that's what we did with momentum. There'll be for sure there'll be a collision problem on the final, and for sure there will be an impulse problem. Oh, one thing I neglected to mention. Anytime you have a product of two quantities that's equal to a third quantity, well, this product is equal to this. Well, that means that if I were to graph it, if I were to graph force as a function of time, the area, like let's say the force increases, reaches a plateau and then decreases. Well, the area underneath here represents the impulse, so therefore it equals the change in momentum. So, those are the main ideas for momentum. Make sure you review momentum, check out your unit summary and all that, and polish up your equation list. But this is kind of the basics of it. Okay, the next one is work and energy. I'll just call it energy. Now, if you've got an object and let's put it on a frictionless surface, you apply a force to it, and that force makes the object move through some displacement. Well, we're doing work, and the work means work is this transfer of energy. Energy is the capacity to change the environment around you. If you've got energy, you can do things. You can make change. And so somebody is making a change. Somebody is changing the motion of this object right here. And this might have some angle. And so the work done, that is the energy that's being transferred into this little cart because some outside agent is applying a force to it. Well, we're transferring energy into it. And that is the force, the magnitude of this force, times the magnitude of the displacement, times the cosine of the angle between them. So this component of the force right here is F cosine theta. That's the part of the force that's doing work. That's part of the force that's transferring energy from one thing into another thing. Okay, so make sure you know. So, hey, I'm going to give you a force, a displacement. You're going to have to figure out how much energy is being transferred through work using that equation. Okay. Now, the result of doing work, if this is the work done by the net force, will cause the object to increase or decrease its kinetic energy. And this is the work energy theorem. Make sure you review that. The work energy theorem, and make sure it's the net force that's doing the work. And of course we said that kinetic energy, this is the energy an object has because it's moving. It's 1/2 the mass times the velocity squared. So if you do work on something with some net force, and that object, we change its speed, we've changed its how much energy it has because it has mass and because it's moving. Okay. So that's connect. So obviously a delta K is K final minus K initial. Now you can also store up energy in elastic materials and in a gravity field. So we have this stuff, we're going to call it potential energy, U sub G. Well, that equals mgh. It's the work that gravity can do because something has height, right? If something has some height, here's the ground, and maybe here's a rock or something like that. It has a certain mass, so gravity is pulling it down with mg, but maybe it can fall down this height, h. So gravity can do this much work. Mg is the force, h is the displacement. So if I hold a bowling ball over your head, that bowling ball has energy. It can affect change to your head. If I were to let go of it, it would come down, turn into kinetic energy, and then plow into your head, and then you've got brain damage and lawsuits and all kinds of problems. But change has been affected in the universe because of that. So this is a way of storing up energy. This kinetic energy stores energy in motion. Gravitational potential energy stores gravity in stores energy in a gravity field, and so on. Now, if you have sometimes you can if there's friction. Let's say I've got a crate that isn't on wheels, and let's say we've got some applied force, and we got some friction force that's opposing our motion. That force of friction can do negative work. Forces can do negative work. If the displacement is to the right, then it can slow down, or I mean, the force of friction here can take the mechanical energy away. If it's trying to take mechanical energy away from the object, that's negative work. When you apply the brakes in your car and you slow the car down, that the force of friction between your wheels and the ground there is doing negative work, taking your energy away. Now, it could also do positive work. When you're at a light and you hit you hit the gas pedal and you go forward, that static friction between your wheels and the road is pushing you forward, and it's doing positive work. Now, I've mentioned this before. We got this stuff called mechanical energy. We use capital E for it. It's by definition the kinetic energy plus the potential energy of the object. If and only if the only force is doing work on your object is gravity or springs, then those forces doing work, they're just changing your kinetic energy into potential energy, or potential energy into kinetic energy, but the sum total of those two forms of energy doesn't change. So if gravity or springs are the only force doing work, then you can say this: the initial energy equals the final energy. And this is a classic roller coaster problem. So go back and I think there's a roller coaster problem on the final. So if you had a certain height and you roll down, you roll down and go up a little hill, the energy you started with is going to be equal to the energy you end with. So set them equal to and then solve for the unknown. Okay. But if you have friction like this, then your mechanical energy is not conserved, because we're turning some of that mechanical energy into thermal energy of the environment. It's being dispersed out into the environment. So be real careful if energy is being dispersed into the environment as heat or sound or whatever. You can't use this. This won't work. All right. Thermodynamics. Whew. Is the next topic on the test, and it's even labeled as such. I label it, the first part is momentum, the second part is energy, and third part is thermodynamics. Thermodynamics deals with the flow of thermal energy. We call it heat. It is a form of energy, and let's see, where did I put it? And if you have a temperature difference, say you've got a block of stuff, maybe ice or something, at a low temperature, and you put some kind of high. Oh, that's fine. I'll put the high temperature over here. So low temp, high temp. Well, here's what we know: heat is going to flow from high to low temperature. Q. So this high temperature stuff loses heat, so we're going to call it negative Q. This low temperature stuff gains heat, so we're going to call that positive Q. It gains heat. All right. Now we've got different ways of creating the result of the flow of heat can have two different effects. It can change temperature. If you're adding heat to something and raising its temperature, then you use this equation. Q equals mc delta T. What is C? That's the specific heat capacity. And this is the mass, that you're heating or you're cooling. But sometimes instead of changing the temperature, we change the state. So we have Q equals the mass again, but then this is the heat of fusion. This is the energy per kilogram it takes to melt something, or how much energy we need to extract to freeze something, to go from a liquid to a solid or a solid to a liquid. Now, sometimes we go from a liquid to a gas or a gas to a liquid. Liquid to a gas, we call that boiling. Okay? A gas to a liquid, we call that condensing. But it's the same equation either way. MHV for vaporization. And if I give you problems, I will give you a problem, but I'm going to give you the heat of vaporization or the heat of fusion. You don't have to memorize that or put that on your equation list. All right. Now, remember the let's see. Now, what happens if these are at the same temperature? What if the heat's going to flow from the high to the low temperature until it reaches what? Thermal equilibrium. And thermal equilibrium is just a fancy way of saying, hey, these two things are at the same temperature, so heat energy is not going to flow. It's done. It's like when your nice hot cup of coffee reaches room temperature, nothing's going to change anymore. Thermal energy is no longer flowing. Let's see, what else? I'm not going to put entropy on the final. There's no entropy on the final, so you don't need to know that. The first law, there's the heat engine. The first law, let's say you have a high temperature. And then we have low temperature here. Well, we know that heat is going to flow from high to low temperature. But if we make this magic little machine, well, it's not magic, it's science, but we call it a heat engine, it's able to extract some of that heat and turn it into mechanical work. But there's always going to be some exhaust going into that low temperature source. So here's our high temperature heat coming out, and then the work. Now, the first law of thermodynamics says that energy is conserved. And what that means is that the heat that flows out of the high temperature has to be equal to the work done plus the heat that flows in. In other words, the stuff that goes in has to be equal to the energy that goes in has to be equal to the energy that comes out. Conservation of energy. Now, the second law, and this is our entropy law, it says that heat flows from high to low temperature. There is no way to make more heat flow from low to high temperature than you made flow from high to low temperature. You can have a refrigerator that can make cool things colder, but that's at the expense of the rest of the universe. The rest of the universe has to have more heat flowing from high to low. Okay, and that's the second law. And another way of saying that is that you cannot have a heat engine that's that turns all the heat flowing into the heat engine into work. There's always going to be some waste heat. So keep that in mind. All right, that should get you through about six multiple choice questions centered around those ideas. Okay, and then half the final is going to be on this last unit on electricity. Woohoo! Electricity. Now, first thing we need to know is that matter comes, we have electrons, protons, and neutrons. Neutrons don't have electrical charge, but protons and electrons do. If I separate protons and electrons, I get I can put a bunch of protons over here and a bunch of electrons over here. They're going to be attracted to each other. They want to get together, all right? Or I could have protons and protons, or I can have electrons and electrons. So make sure that you know that unlike charges attract, but like charges repel. Now the equation that describes how much force these point charges apply to each other is given by Coulomb's law. F equals K, Q1, Q2 over R squared. It looks very much like the law of gravity. Same mathematical structure, but here K is equal to 9 times 10 to the 9 billion newtons of force, and then Newton meter squared per Coulomb squared. So this is a constant of nature. That's the electric constant, and it tells us how strong the electric force is. It turns out to be very, very strong indeed, much stronger than gravity. But there's two kinds, and so if you're an electrically neutral object, you don't feel any electric force because they're all canceling each other out. All right. Then we defined electric field, and it's unfortunate that we use the capital E because we use capital E for mechanical energy as well. But if I put a vector hat on it, you can be sure that that's electric field. You take the electric force and divide it by the charge you put in an electric field. So let's suppose I have an electric field, and I give you a problem where there's a uniform electric field. If I put a charge right here, a certain charge right there, how much force is it going to have? Well, that's what electric fields do. Electric fields apply forces to objects that have charge, that have a net charge on them. That's what they do. Now we draw electric field lines to visualize them. And electric field lines, the number of lines is proportional to the amount of charge. I mean, this is what caused the electric field. I separated some electric charge. Then I put another charge, we call it a test charge, Q naught. I put that in the electric field, and now it's going to feel a force. And the force is equal to the charge times the electric field. So this little expression right here you're going to use. You're going to use this one to figure out the magnitude between charges, and then this you can get the electric field somewhere. Now, let's see what else. Oh, now I can do work against an electric field. If I can look, if I take a positive charge right here and I push it against this electric field, I put it right over here. I had to do work to do that, right? I had to put energy into it. And how much energy I put into it? Well, it's equal to the charge right here times the electric field times delta X. Or sometimes, actually, I think in the book they call it D. Now, if I go against the electric field, I'm gaining potential energy. But if I release this charge, boom, it's going to go boom. So it's just like a rock falling down a gravity field. This is like a charged particle falling down an electric field, so it's going to lose electric potential energy. And so if I take this and divide it by the charge, I get my definition for voltage. So voltage, or a change, I should call it a change in voltage, is equal to negative E times D. Now what does the negative mean? Well, the negative means that if I do work against the electric field, I'm gaining. So if E and D are in the opposite directions, then I'm gaining potential, but if E and D are in the same direction, I'm losing potential. Now look what units I have here. I've got newtons per coulomb for electric field times meters for distance. That's joules per coulomb. And a joule per coulomb is called a volt. So that's voltage. Okay, now I got about 3 minutes left to talk about circuits. But we've just been reviewing that, so I don't think I need to spend as much time on it. If I have a a battery, here's the voltage of a battery. What a battery does is it establishes an electric field that pushes charges through a wire. And how much charge you get pushing through that wire, that's current. And that's equal to how much charge goes by per unit time. There is a question on a multiple choice question where I ask how much charge flows by in a certain amount of time. Well, if you know the current, multiply it by time, and that's how much charge went by. So you're going to need this equation. Charge per unit time, that's coulombs per second. That's an amp. Now, how much voltage do I need to get 1 amp to flow through this thing, like a light bulb or a toaster oven or a cell phone or something that's going to use the energy that this battery pumped into the electricity? Well, we call that resistance. Resistance is how much voltage I need per quantity of current. And that leads us to this expression, V equals IR. That's Ohm's law. Now, if I have an equation where I have 2 resistors, well, look what I've done. This is R1 and R2. Now I've got the current has to go through both of them. So the total resistance is equal to R1 plus R2. But if I've got this, if they're in parallel, well, now they have the same voltage, but the total resistance is less. It's 1 over R1 plus 1 over R2. We derived that, so I'm really just kind of cramming this down your throat at the last minute. Also, power. Power through a resistor is equal to the current through the resistor times the voltage drop of the resistor. But if you substitute in Ohm's law, you get I squared R. If you substitute in for the current using Ohm's law, you get V squared over R. So these 3 equations, or these 3 little expressions, I times V, I squared R, and V squared over R, all give you how much energy per unit time is escaping into the world through a resistor. All right. Well, that was a whirlwind of review. Study, prepare your equation lists, look over your unit summaries, do practice problems, and I will see you on Monday. Or if you're in my 7th period class, I'll see you on Tuesday. That is all.